the application of Schrödinger equation. We know that there are two types of Schrödinger equation we already read. One is the time independent one and another is the time dependent Schrödinger equation. You see here, this is the time independent Schrödinger equation. Minus h cross square by 2m due to psi x dx2 plus vx psi x equals to E of psi x. Now, what is E here? E is the energy of the particle and the psi x is the wave function associated with the particle. So we are now dealing with a particle having mass m, momentum p, energy E, and when moving in a potential field V. Now for this particular situation, the potential field V is described as V equals to 0 when x belongs to L and 0, and V equals to infinity when x is less or equal to 0 and when x is less or greater than L. That means first we have to, if we have this kind of potential field and if a particle is moving in this kind of potential field, first we have to sketch the potential field to find the Schrödinger equation. So what is our task? Initially, uh, we have to sketch like this. Here we have sketched it. This is the x-axis from minus infinity to plus infinity, and we have tagged x equals to 0 and x equals to L to points, and over that we have drawn the infinitely large potential as given here, that v equals to infinity when x equals to 0 and x equals to L and beyond this. That means here this goes to infinity. In the y-axis we have plotted the potential, and x less than 0, that is the left hand side of this, and right hand side of L again at L, and right hand side of L v equals to infinity, and v equals to 0 here when x is belongs to 0 and L. So between x equals to 0 and L, v equals to 0. So what is our aim? Our aim is to find the structure of the wave function and to find the energy values for different energy states. That means for the ground state, for the first excited state, what will be the energy of a particle which will be moving in this kind of potential field. So to study that, first we have to construct a Schrödinger equation appropriate for a particle which is moving in this kind of potential field. So that Schrödinger equation which we have mentioned here, this is the general version of the time independent one. Now here we have to modify this Vx. That means the Vx is given here. So we have to modify according to the problem or according to situation given, and then we will get modified Schrödinger equation. So now here we see, let us first find that where the particle can exist in this kind of uh, potential field. So we know that in a region, force-free region, or at a v equals to 0, it is very normal, or it's a normal situation that a particle can exist in this kind of situation. So we admit that this Ix exists when v equals to 0. But what about when v equals to infinity? Do the particle exist in this region? Let us consider the yes, that particle exists here. So if the particle exists in a region of v equals to infinity, that means the particle must possess infinite amount of energy, but it is unphysical. Then let us think it in another way, that we know the particle exists here inside these two infinitely large barrier. Well, so if the particle exists here, and if the particle wants to overcome this barrier, if the particle wants to give a huge jump, then what will happen? The particle then must have to possess again an infinite amount of energy to overcome this barrier, which is again unphysical. So there shouldn't be or will not be any trace of the particle in the region of v equals to infinity. So if there is no particle, there is no wave function, so psi should be 0 in this region. So if psi equals to 0 where v equals to infinity, then psi or the particle is only exist inside this or inside these two barriers. And if you see from upside down, it will look like an infinitely deep well-like thing or well-like structure. Therefore, these kind of problems are known as one-dimensional infinitely deep potential well. Now we are going to modify the Vx of this Schrödinger equation to find the exact Schrödinger equation for this purpose. That we have done in this next page. Let us see here, if we make v equals to 0, why we are making this 0? Because we know that the particle can only exist where the potential is 0. So psi x exists. Otherwise, there is no particle where v equals to infinity. So d2 psi x dx2 plus 2me h cross square psi x equals to 0. This is our Schrödinger equation for this purpose. Now let us consider this term 2me by h cross square equals to k square. So if it is k square, that means it's obvious k equals to 2me by h cross square root under of this. So this is the second order. This is a kind of second order differential equation you can see. And the probable, of course, we know the solution is the psi x, and the probable construction or the form of the psi x may be psi x equals to a cos kx plus b sin kx, where a and b are two constants. And we have to find the values of a and b to find the proper or exact form of psi x. How to find this one? So we are going to consider the boundary values. What are boundary values? Boundary values means we have already seen that when x equals to 0, the v equals to infinity, and when x equals to L, the v equals to again infinity. And in these two regions and beyond this, the v equals to infinity, and in these regions, the psi equals to 0. So we are using these two conditions as the boundary conditions. Let us consider the first boundary condition when x equals to 0, v equals to infinity, and psi x equals to 0. So when x equals to 0, let us put this one here, the psi x 0 in this equation. So if we put 0 here, so this will give us 0 equals to a plus cos 0 1. So a will exist and sin 0 0. So we will disappear. So this a equals to 0. We got a equals to 0. So we are able to found the value of one constant a, that is equals to 0. So this equation now reduces to psi x equals to b sine kx. Now let us consider the second boundary condition where x equals to L, v equals to infinity, psi x equals to 0. So if we put x equals to L and psi x equals to 0, this will give us b sine kl equals to 0. But b not equals to 0. Why? Because if b equals to 0, again we already found a equals to 0, then there will be no existence of the wave function. But we know that the wave function exists in a region between 0 and L, that is in the region of 0 potential. Therefore, sine kl equals to 0. And this equals to, of course, always sine n pi when n is an integer. So we can write kl equals to n pi, or k equals to n pi by L. Now from here, we can also write, we know that k equals to 2me by h cross square. So k square equals to n square pi square L square equals to 2me by h cross square. So from here we can write E equals to n square h cross square pi square by 2m L square, where n is the integer. This is actually the quantum number, and it is giving us the n equals 1, 2, 3, etc. So we already put a suffix here that is en. So this will give you the different values of energies from the ground to the different excited states. We are coming later now. Now for the particle which is already been trapped in the kind of the infinitely deep potential well of with L, the psi x equals to b sine n pi x by L. Just putting the value of k here, this is b sine n pi, x by L. We are putting the value of k here. Okay, so now we have still we have to find the b. So how to find the v? To find the b, we have to normalize this wave function. So this is the standard normalization procedure because we know that the particle do exist between x equals to 0 and L. So this is psi star psi dx equals to L. And as this is psi to psi dx equals to L, from here if you do the calculation, you will see this will b square by 2 to sine square n pi x by L dx, etc. And ultimately you will get b equals to root under 2 by L. So if we put the value of b in this in the equation, again here we have the equation that psi x equals to b sine n pi x by L. So this will be psi equals to root under 2 by L sine n pi x by L. So this is the structure of the wave function for a particle which is trapped by infinitely deep potential well. And here we again are going to put the suffix n because this will give you the probable eigenfunctions. Here we are getting the eigenvalues for different energy values. So E1, E2, E3 and the corresponding eigenfunctions will be this will show the corresponding eigenfunctions, that is the psi 1, psi 2, psi 3, etc. So as we have mentioned that this n the integer, this starts from 1, 2, 3. We are excluding the value 0 because if we put 0 here, then again the wave function will disappear. So as it starts from 1, so the ground state for the particle which is confined inside this infinitely deep potential well, that will be E1. So the ground state energy, you have to remember that the ground state or the zeroth state energy is not 0 actually. That is U1 equals to h cross square pi square 2ml square, and this is the ground state energy. And when we are going to look over the first excited state, we have to put here 2. So that will give you 4 h cross square pi square by 2ml square, etc. And the corresponding eigenfunction is psi 1, and this will give you 2 by L sine pi x by L. Again, now we are going to plot it. What we are going to plot? We are going to plot the wave function psi x. So if we plot it, we already have seen the values of psi 1, psi 2, psi 3, etc. If we put different n values, we will get these values. So we already have seen when if we put x equals to 0, this will give you 0, and again x equals to L, this will again give you a 0. So we obtain two nodes here. One is at x equals to 0 and another is at x equals to L. And this will be picked over L by 2 because this is a sine function and the maximum value this will give when this will be pi by 2. So the ground state will look like this. Again, if you calculate this one for the first excited state, you will get these kind of structure because this is a sine function. So this will be peaked over L by 4 and 3L by 4, and we will get a positive and negative peak. If you calculate here, this is given and you can see it again. And for n equals to 3, this second excited state, you will get 3 peaks like this. The values are given here. And in the second figure here, this is the figure for mod of psi x square. This is the probability density. So this will look like as it has shown here, and this is for the first excited state, this is for the ground first excited, and the second excited state. The calculations are given here. You can go through this one, and this ends the first application, that is the one dimensional application of the Schrödinger equation.